everyone. Thanks for having me. Thanks for staying for the last session. We're almost there. My name is Chang. I'm a final year PhD student at Northwestern, working with Adam Miller. And today I'll be talking about our research, our ongoing experiment of combining the early and late time observations to understand the progenitors of type 1a supernovae. While type 1a supernovae seems to be one of the most intensively studied transient for the past few decades, ironically, we still don't know how exactly they explode. Probably the only consensus is that the classic scenario where the white dwarf has to accrete until the Chandrasekhar mass before they can explode cannot explain the full picture, and at least a substantial fraction of white dwarfs explode way below the Chandrasekhar mass. But a sub-Chandrasekhar mass white dwarf itself in isolation cannot explode, so there has to be some hammer to trigger them in a dynamical way. So one of the most popular scenario is known as the helium shell double detonation scenario. So essentially, we would expect the white dwarf to have a helium shell, and for some reason, there is an original detonation in the helium shell, which would then propagate along the shell and send a shock wave inwards the carbon-oxygen core. And eventually, a secondary, which is the primary detonation, will explode the entire white dwarf, leading to the type 1a supernova that we see. Nevertheless, disentangling double detonation sub-Chandrasekhar mass white dwarfs from near Chandrasekhar mass explosions are very tricky, mostly because they can produce very, very similar observables when a supernova peak in luminosity, which is when we got most of our observations. But still, there are some clues. For example, in the outermost ejecta, we would expect some helium shell as well as helium burning ashes. So in a double detonation scenario. For that reason, if we go early enough, a few days after the explosion, probably we will see some difference between the two scenarios. On the other hand, since the density of the sub-Chandrasekhar mass white dwarf is much lower, the nucleosynthesis yields in the innermost region will be fairly different than the near Chandrasekhar explosion. So the abundance of the heaviest elements, which is essentially the stable nickel, can be another hint of the sub-Chandrasekhar mass origin. So this idea of combining very early and very late time observations has inspired our ongoing experiments of collecting, say, early light curves and nebula phase spectroscopy for ZTF supernovae. Essentially, for every ZTF 1a that is bright enough and has good enough early time light curves, we'll try to get a nebula phase spectra, which is enabled by the unique power of the amazing Keck telescope, and we're mostly using the LRIS instruments. So quantitatively, we're essentially making use of a unique property of the double detonation scenario. So all those multidimensional hydro simulations predict that double detonation is intrinsically very axisymmetric. Specifically, if we're observing from a sightline that is close to the original detonation point, that at early times, we would expect the light curve to evolve from a red color to a blue color. And if we wait for a couple of hundred days for the iron core to be revealed, as you can see from the sketch, we would expect the iron core to be receding from us so that the iron lines will be redshifted in the nebula spectra. So this is essentially the core correlation that we're exploring in our sample. I'm not diving into super details of how we extract the properties of the early light curves because I cannot wait to show you our Keck data. But the key takeaway is we're still fitting them into the classic power law rise for the multi-band ZTF light curves, but rather than fitting them separately, fitting individual light curves separately, we are assuming that each light curve is drawn from a hyperdistribution that is intrinsic to the 1A population. And then we fit all the supernovae simultaneously. By all the supernovae, we mean not only our small sample of 35 objects, but also the entire ZTF DR2 sample, which has a decent early time light curves. So there are more than thousands of light curves. Here is where I'm essentially showing that the rise time versus the X1, which is essentially the broadness of the light curve. We can see that our small sample is well distributed all over the phase space, consistent with the entire ZTF DR2 normal 1A sample. Hopefully, this means our sample is unbiased. But taking the unbiasedness actually has a pretty high cost, especially in the nebula phase when a supernova has substantially faded. At this phase, as you can see, most of the so unlike many of the previous samples, we're not deliberately excluding targets with significant host galaxy contamination. That means when we spend, say, an hour of LRIS time to get a 2D spectrum, the classic method would be, okay, first we mask the trace of the supernova, then we select some local sky region, and finally we do some linear interpolation of the flux in the local sky and estimate the galaxy flux as the sky background that is blended with a supernova. But in this case, given the curvature of the galaxy background, as you can see, there is just tons of galaxy residual in a supernova spectrum, which prevents us from doing precise inference of the line ratios, which we really care about. This is why I wrote this software called HostUp-GP, which is essentially using Gaussian process to model the 2D spectrum by leveraging the archival images of the galaxy. So in the classic method, by doing this linear interpolation of the local skies, we essentially assume that we don't have any prior knowledge of the galaxy flux at all, which is not true, because at least at these couple of wavelengths that are observed by previous surveys, such as pan-stars, we know what is the galaxy flux distribution along the slit. So the software will automatically start from these 5 galaxy flux distribution measurements to build a smooth prior as the galaxy flux distribution as a function of the wavelengths. And then we'll use another Gaussian process to implement this prior and to model the eventual 2D spectrum. And with that, we can get a much better estimate of the galaxy flux blended with a supernova. So we have been tested in a couple of cases. Probably one of the most interesting cases is just the spectrum I just shown. It's from a peculiar hydrogen-4 supernova, 19EIX, which can be either a core collapse supernova with its envelope stripped, or it can be a double detonating type 1a supernova exploding of a white dwarf. With early time data set, it's just very, very hard to tell. But at some point, Christopher took a late time spectrum showing the interior region. And with the re-reduction of these LRIS spectrum, we find that the resultant nebula phase spectrum of this source is highly consistent with a 1A, showing all those iron features. And we're even able to precisely model the line ratios, the element abundances, showing that the abundance of the stable nickel is extremely low in this case. And the stable nickel, as a reminder, is a probe of essentially the central density. So this is, again, consistent with a subchandrasekhar mass double detonation scenario. So eventually circling back to my sample, is still the data reduction and data analysis are still ongoing, but there are already some interesting correlations. Here I show the early time color evolution versus the iron core velocity, and on the right panel is essentially the abundance of the stable nickel. On the left-hand side, for our entire sample, definitely I won't draw any correlation. That is not allowed. But what is more interesting is that if we're specifically looking for objects with a low stable nickel abundance, the correlation that we expect seems to appear. There seems to be some correlation between the early color evolution and the iron core velocity. So it seems to suggest that at least within a subpopulation of the entire 1A family, we do expect to see some axisymmetric explosion in their ejecta. I will stop over-interpreting the results because this is warned by some theorists. But just to give you some key takeaways, we may still be a little bit far from understanding the entire picture of the type 1A supernova progenitors. But as we're getting a much larger sample, and especially in the near future with Rubin, it is really how we do the inference properly with a larger sample. So I do believe that for the future of the type 1A progenitors, we'll need to combine, say, observations at very different phases early time, around maximum, late time, and it will be even better if we can also take into account the host galaxy properties. And additionally, late time, nighttime nebula phase spectra will still be critical. And with the software that we have developed, you just don't need to throw away your favorite supernovae, even if it's not a 1A, even if it's not a supernovae. You just don't need to throw it away when it has a significant host galaxy contamination. With LRIS being with LRIS continuing to be one of the great instruments for transient spectroscopy, hopefully our software will be useful for the entire time domain community. With that, thanks again for having me here. I'm happy to take any questions.
Hello, everyone.